Okay, we're going to talk about pressure today. We've been talking about pressure. We did a lab and a lot of whiteboardings about the effect of changing volume, amount of particles, and temperature uh, it, on pressure. And if you'll remember, the first part of our behavior of gases lab was where we held the amount of particles and the temperature constant in our syringe. And we started with a volume of 20 milliliters, and we crushed the syringe down, lowering the volume as the pressure went up. And this is an inverse relationship. If the volume went down, the pressure went up. If the volume goes up, the pressure goes down. The second part of the lab was where we had to kind of work at this a little bit, but we kept the volume and the temperature of the gas constant while changing the number of particles in the syringe. We put different amounts, but we would always return the syringe to the same 10 milliliter volume. And we saw that as the number of particles rose, the pressure rose. And this should make sense to us because you know that if your car or bicycle tire has low pressure, well, you pump more air or more particles into it. The third part of the lab is where we held the volume and the amount of particles constant in that sealed flask. And we started with really hot water and we cooled it down and we watched the pressure go down. So we noted that as the pressure went down, or as the temperature went down, the pressure went down, and as the temperature went up, the pressure went up. Another one that we didn't do in lab, but we talked about in whiteboarding before the lab, was that if you could hold the amount of particles and the pressure constant, if you increase the temperature, those particles would start moving around faster and they would push against the sides of the container like a balloon or something where the volume could change. As the temperature went up, the volume would go up. And now let's talk a little more in detail about the math of pressure. Okay? We can easily talk about pressure on a macro scale, which means a big scale, like you see a balloon and you can see that the balloon's volume gets larger or smaller, or you can tell the temperature of the balloon. Or we can talk about it on a micro scale, which is what we like to do, which is the particles inside the balloon. Okay. Pressure on a macro scale is like the amount of force exerted over a given area. Like here in America, we like to use pounds per square inch. And what that means is literally how many pounds of force are being applied to every square inch of, in the picture here, a tire, or it could be you, or a balloon, or anything that is surrounded by a gas. But in essence, it's all about the little particles moving around like inside a tire, and they're having collisions with the outside of the tire, and they're actually pushing the tire outward. And normal tire pressure, you would fill a tire about 32 pounds per square inch, and that literally means every square inch of that tire is having 32 pounds of force applied to it from those particles moving around inside the tire. But it's not just what's inside the tire, there's also particles of the atmosphere pushing down, and those particles are colliding with the outside of the tire and applying a force in the opposite direction. So the particles inside the tire, or balloon, or blimp, or whatever, are pushing outward on the tire from the inside, and the atmospheric particles are pushing inward on the tire. And it's all about those particles colliding with the sides of the container, in this case the tire. And it's that atmospheric pressure that we're going to kind of focus on here a little bit. It helps us to do our math. It's the basis for our being able to convert pressure units. It is the atmospheric pressure that we all feel. And this is because we are at the bottom of about a 20-mile deep pool of air particles that are moving around, and all that weight of all those particles, all that mass pushing down on us. There's several different units of pressure. Some of the standard ones are, standing at sea level is called 1 atmosphere of pressure. The units are atmosphere. And that's equal to 14.7 pounds per square inch, an American system. And that's also equals to 760 millimeters of mercury. We'll get a little more into that later, but that means that the atmospheric particles are able to push a column of mercury 760 millimeters up into the air. That's the force of the atmosphere. That's also equal to 760 torr, and that's equal to 101.3 kilopascals. And the kilopascals are what's important to us. That's the international system's units for pressure, or kilopascals. So all these numbers across the bottom of the screen are the standard atmospheric pressure in these different units. They're all the same pressure, they're just different units. Measuring pressure. Okay, standard temperature and pressure is all of these units. The 1 atmosphere, the 101.3 kilopascals, the 760 millimeters of mercury or torr, and the 14.7 psi. That is standard pressure. And they are all equal, and this will be our conversion factor when we're doing math. And standard temperature for gases is, I know it seems kind of odd to think because normal room temperature is about 20 degrees Celsius, but for doing the math, standard temperature is 0 degrees Celsius, which is the same as 273 on the Kelvin scale. And Kelvin is going to be important to us because it's the only absolute true zero scale. No motion means zero. So when we do our gas equations and gas laws, everything has to be in Kelvin. So standard temperature is 273 Kelvin, standard pressure is 101.3 kilopascals. An example of converting units. Okay, so the example is your local weatherman's forecast predicts a coming thunderstorm. He lists a barometric pressure of 715 millimeters of mercury as evidence for this prediction. You know that they always say low pressure means bad weather is coming. I want you to convert this pressure into kilopascals. Okay, we're going to start with what we're given, 715 millimeters of mercury. And it's just a normal unit conversion. You've seen these before in math class and other science classes. We're going to multiply that by the ratio. And we have millimeters of mercury, and the question is asking us for kilopascals. So we're going to multiply our original number by the ratio of kilopascals to millimeters of mercury. If you note, I put millimeters of mercury on the bottom and kilopascals on the top because that allows us to cancel the millimeters of mercury, and the only units we have left are kilopascals. So now we take 715 times 101.3 and we divide by 760, and we get our answer as 95.3 kilopascals. It's important to remember that all we did was convert the units from millimeters of mercury to kilopascals. We didn't change the pressure, we didn't change the value of the pressure. 715 millimeters of mercury is the same as 95.3 kilopascals. Okay, and now some devices that, frankly, this one isn't very important to us anymore. A barometer is a device that's used to measure atmospheric pressure. And basically, it's an evacuated glass tube sitting with the open end in a pool of liquid mercury. And it's important that the tube has no particles in it. It's a vacuum. The atmosphere, all those particles, that 20-mile deep pool of particles is pushing down on that mercury. And it pushes down with enough force to lift that very heavy, very dense mercury 760 millimeters up that tube. So the atmosphere has that force, it has that pressure. It's the same pressure that you feel from the atmosphere. You're just used to it. Now this one is a little more important to us. This is called a manometer. It's used for measuring pressures inside of gases inside a sealed glass bulb. And it has well, here. So you have a gas sealed in this bulb, this container. And you can either heat or cool the gas, causing the particles to speed up or slow down and changing the pressure that they exert on this glass bulb. Okay? The other end of the manometer is open to the air pressure. So whatever the air pressure is in the room, those particles are able to push down into that U-shaped tube. Okay? And there is a fluid, usually mercury, a heavy liquid, in the U-shaped tube, and it starts equal. You'll notice that they're both at 95. That's the height of the mercury in the two tubes. Okay? And if the gas pressure, if you heat up the bulb, the pressure of the gas in the bulb here is going to increase, and it's going to shove the liquid up the tube away from the bulb, and it's going to make an imbalance in that liquid mercury in the U-shaped part of the tube. Okay? And that difference in the height of the mercury column is what you'll use to actually calculate the pressure of the gas in the bulb. So let's do an example. I'm going to consider, I want to know what the pressure of the gas in the sealed part of the manometer is. That's the little particles moving around in the bulb. It says the room pressure is 730 millimeters of mercury. That's what's pushing down this open end of the manometer tube. It's pushing down on this liquid mercury. Well, we need to know that it should be pretty evident that the pressure in the bulb is greater than the pressure in the atmosphere surrounding it, because the liquid mercury has been pushed down the tube away from the bulb. So it's been taken, the liquid mercury has been taken out of balance by this increased pressure in the bulb. Okay, so these particles are literally pushing down on that mercury and pushing it away from the bulb. That change in height that you see, it's 84 here on the bulb side and 127 on the side that's open to the room. All you literally have to do is measure that height in millimeters, and that's where the millimeters of mercury comes from. Okay, so the change in height, that's 127 on the high side and 84 on the low side. So the difference is 43 millimeters of mercury. Now we know that the room is 730 millimeters of mercury. We know the bulb is higher than that. So we take the 733 millimeters and we add the 43 millimeters of mercury to that and get 773 millimeters of mercury. That's the pressure in the bulb.